So what I thought I would do was more lecturing, get all the lecturing out of the way, and then next week will be sort of all lab time. Because I'll answer questions up here for the recording next week if anybody wants to ask me sort of a question up here, or if I decide the question is the question a lot of people might have, I might just bring it up here even if you ask it at your seat. So I'm going to try to go ahead and do the Unit 11 lectures so that you have all the lecture under your belt and you're ready to do the labs. I want to first continue where I was, sort of almost repeat it and finish it. I think that might have been 10A. No, not 10A, maybe 10B. So we were doing this toward the end of yesterday, and now I'd like to sort of do it again and finish it this time. Okay. So we are mapping out this instruction, the microcode instructions, the very lowest level, the instructions that work in conjunction with the hardware. And these are underneath the assembly level instructions. So if you wrote any assembly in your architecture course and you thought that was low, we're even lower. So you take a simple instruction at the assembly level, like take a number and put it into the accumulator so that you can do some calculating with it. That has a number of steps at the hardware level. And the first 3 steps are known as the fetch, and that is just figuring out what it is we wanted to do in the first place. Because we are running code, and so it is programmable, and therefore we don't know, the computer does not know what it is going to be told to do until it reads the code out of the memory. So the first instruction was to get the value of the program counter over to the memory address register. So I'm going to repeat the first part and then finish it this time. Okay. So the first action over here in my picture is to move from the program counter to the memory address register. So I say who's involved. First I say control is always involved. And then I say in this first step, also involved is the program counter, which I'll sometimes call PC, and the memory address register, which I'll sometimes call the MAR. And so then I ask the question, who's driving the bus? Who's putting the value on the bus? That was the program counter. And who's taking the value off the bus? That's the memory address register. So that was step 1. Step 2 says the increment state. The program counter is incremented. So when the program counter is incremented, there's no action on the bus. It's just control telling the program counter to increment. So who's involved is the control and program counter, and there's no action on this center sort of data bus. Some control connection that we're not showing in this picture, but there's no bus here. Then the third step is to take the current line of the program and put it into the instruction register. Oh, I didn't do my arrows, I'm sorry. So the first arrow, the first step arrow was 4 and 6. And then down here, there's no arrows, none of the numbered arrows. There's some control that is not shown. Okay, step 3 was to move the line of code, which is in memory, into the instruction register. So 7 tells us the address of the data, which is an instruction, and then it moves from memory to the memory data register, and then out onto the bus and into the instruction register. So who's involved? The memory address register is telling us where. The memory is telling us what is at that location. Then it moves through the memory data register. I'll call the MDR. And then it moves into the instruction register. Who put something on the bus? MDR. Who takes something off the bus? The instruction register. What are the arrows? There was a 7, a 9, a 10, a 13. 7 was telling us the address, 9 was the data passing through the data register, 10 was it moving onto the bus, and 13 was it moving into the instruction register. So those are my first 3 steps. Now I know what I'm doing. This is always the same because I don't know what I'm doing, so it can't be any different until I know what I'm doing. And so this orange part now is the fetch cycle always the same. And as I said the other day, when I give this question on the test, it'll be a different instruction, but this part you'll get completely correct because it's always the same. In fact, this is the last time you'll see me describe these first 3 steps, because in, like, if I give it to you in lab 11, which I do, then I won't give you the fetch cycle steps because they're always the same, so why repeat myself? And I'll just jump right into the execution. Okay, so that's as far as I was the other day. Now let's read what the execution cycle. So the instruction was a load, and there's a what we call an opcode and an operand. There's something that says what to do, and then there's a little piece of data involved with it. And in this instruction, that piece of data is an address. So we're going to move the address to the memory address register. And the instruction and its data are now in the instruction register. So we're going to move the data part of the instruction out of the instruction register and into the memory address register. That's our next step. In the execution cycle, the instruction register is telling control what it is we're doing now. Before we were sort of on autopilot. In the fetch cycle, we're kind of on an autopilot, and we need to just do what we always do. But now that we have the instruction, we have to differentiate to do the actual instruction. And that communication between the instruction register and control is on 14. And so here I'm going to say 14, 14, 14. As when I execute, I need to know what I'm executing. So that's 14. And then I do here a 12-6 while I'm down here. And then who was involved? The instruction register. Write it out. Instruction register, or IR. And memory address register. Sorry, I said it was MA. And who's putting their information on the bus? The instruction register. And who's taking it off the bus? The memory address register. In terms of who's involved, once I'm in the execution cycle, the instruction register is always involved. So I'm going to put IR here. So here, I said I put control. Control's always involved. And during the execution cycle, the instruction register is always involved. Okay. So, but now let's look at the specifics of step 5. So that was step 4. Step 5, the value at the address, I just put in an address. Now the value at that address, which is in memory, is loaded into accumulator A. So I set up the address. I'm using that address. I'm getting the data at that address. I'm moving it out onto the bus, and this time into the accumulator. So who's involved? Memory address register, the memory data register, and the accumulator. Who's putting their, yes?
So essentially, like if we had this on the exam, like the steps 1 through 3 would be the same, but you would change.
Steps 3 will be the same. I won't even tell them to on the test. Like in the execution cycle, I have to give you some description because you don't know what the instruction does. But the fetch cycle is the first 3 are always the same. I won't change I might add, you'll see in lab 11, I add something. I add a stack pointer, but I won't take anything away or I won't change the numbers. So the first part is just a copy, get it half right. There's enough of a pattern in everything else, then it's worth a guess. That you should be able, well, figure it out. Some parts are subtle and some parts are like always the same. Like when you, well, I'll show you, let me finish this one and then I'll show you sort of where one of the patterns is. Okay, so who is driving the bus? The NDR. Who was taking the thing off the bus? The accumulator. What are the numbers? 7, 9, 10, and this time 15. And now I have the number in the accumulator. And on this instruction, step 6 is just to do nothing. So it's still, the instruction register is telling me it's a load, and then the control says for everybody else not to do anything, but control is still, I don't know, quasi-active. Active just means I just say involved. So the control is telling everybody not to do anything. So there's nothing on the bus, nothing here, and just the 14. Okay. So that is that. Now the next instruction is an add. you have to sort of say, I tried it, and then I will talk to you and see how close you got. But you have to try it. You're not just gonna say, will you do the ad? Maybe next week, but at least somebody's gotta try it. You know, somebody might try it and then I'll talk to everybody, but at least one brave person must try it. Okay, patterns. When you deal with memory, and programming is always going back and forth to memory, it's always a two-step process. You have to set up the address and then work with the data. So we saw that in 1 and 3. Here's us setting up the address, and then here's us working with the data. And then we saw that again. Here's us setting up the address, and here's us working with the data. Now, I liken this, I have students who work at a restaurant. So here is the memory is, here's my analogy, it's kind of crappy, but it'll do. The memory is like a restaurant. We have the staff, and then we have the customers. So the address is like the staff. They have to arrive earlier and they come in by a different entrance. So they're not, it's a fancy restaurant. They're not allowed to come in the main door with all the fancy dressed people. They've got to sneak in some back door. So the memory address register, whenever we're dealing with, whenever we're serving food, whenever we have this memory, we need the staff. They arrive first. That's the address. They come in through, the address comes in through 6 through the memory address register. And then we have the customers, and they work with it. They come later, and they come by a different entrance. Okay. What else? Just little arrow sort of things. 9 and 10 are a team for when I'm reading. So if I'm reading, it's 9, 10. So I was reading the code. So it was 9, 10. And then I was reading some data, 9, 10. If I were writing, it would be 11, 8. So 9, 10 are a pair for when I'm reading something from memory. 11, 8 are for when I'm writing. So if something is going, if I get some answer and I'm writing it to memory, if I'm doing what's called a store, or when we are playing around with the stack, then what we call a push, then we're putting something into memory, and then it would be 11, 8. So the read is a 9, 10, the write is an 11, 8. Anything else at this point? Questions? All right. So, but even if I said, okay, here's a load the accumulator, and if I gave you a store the accumulator, you would still probably have the address part. So of course you copy the fetch part. That is going to be exactly right. But say I give you a store and you had a load, and all you do is you slap down the load and say, I don't understand the store, but I know a load, let me throw that down. Well, one of the steps in the store might be to get an address. To store it where? Where am I going to store it? I'm going to store it at some address. Well, then you would get step 4 right because that's address. You would have step 5 wrong because you'd have the direction wrong. You'd have step 6 right because they would both be resting on the 6th step. So with if you follow the flow, it's not too bad. And if you know the little patterns of how you deal with memory, you can usually fake it. There will never be something driving the bus without somebody reading the bus. That doesn't make sense. So there are always two things here. 6 is a one-directional arrow, so you can, the memory address register can read from the bus. It will never write to the bus. Whereas the other things, the program counter can enable, put a value on the bus, or load, take a value off the bus. The same for the MDR, the same for the instruction register, the same for the accumulator. The ALU only puts stuff on the bus. We don't put answers into the ALU. The ALU gives us answers. So pay attention to the arrows. And I already told you the other day, these are important in terms of having a computer, but they're never going to be part of the answer for me. So if you were talking about input ports or output ports or B or C, forget about it. You're wrong. You're barking up the wrong tree. Yes. Different command. So down there. So now here's the add. I don't even tell you the fetch. It's above. And then I say, here's what we're doing. Read the instruction is an add command and an address. Take the address to the memory address register. Take the value at that address and put it in temp. Then you have a number in accumulator A and in temp, and add them up and get the answer and put it in the accumulator. If you draw the arrows, it usually helps.
Yeah.
So I won't do it for you until you try it, and then we'll talk. But it is, 75% the same.
Yeah.
You'll get it half right. If you are brave, you'll get it 2/3 right. And then if you're brave and smart, you'll get it right. Okay. And if you just practice, it's usually, it's the first time it's like, what in the hell is he talking about? And then it starts to make sense. All right. Any other questions? So you're ready to do that. Lab 10 is, you're ready to do that. Let me start talking about some 11 stuff and see how far I get. Let me talk about inductors. Hopefully I'll get done inductors. This is me going through some of the stuff on YouTube. Then this one is me, this in inductors _1 is a PowerPoint with voiceover, but instead of doing a demo, I stole a demo from YouTube, so I can't post it on YouTube because I stole from YouTube, and they know that. So they won't let me post that on YouTube. That's why I just posted as a PowerPoint. Here's the PowerPoint that I'll go over now that doesn't have a voiceover. So we're going to talk about one more device, the inductor. And I'm going to go through the theory fast. And so there are electric fields and magnetic fields out in the world, and they are related. And so an electric current gives rise to a magnetic field. So physicists have discovered that in like the 1900s. So if you have a wire carrying a current, then the magnetic field goes around it in a circle. and it depends, the direction of the circle, clockwise or counterclockwise, depends on the direction of the current, and that is given by a thing known as the right-hand rule. So if you stick your thumb in the direction of the current, the thumb of your right hand, hence the right-hand rule, then your fingers curl around the direction. So this indication here, that gray circle with the X, that's a wire, and the current is going into the slide. The arrow, that cross is meant to be like the feathers of an arrow, the sort of back of an arrow. So the arrow is going in. And then if I take my right hand and put my thumb into the page, my fingers curl around in a clockwise direction. What I usually try to do is, when I'm teaching the right-hand rule, it's like turn my back to you so you're not mirroring me, because then you'd be, my right hand would be your left hand. So I'll turn around my back to you. Am I still? So if I put my fingers into the board, my fingers curl around clockwise. All right. If the current goes around in a ring, in a loop, then we can figure out the magnetic field around each little part of the loop based on what we know before. And if you look at these, all these B fields, you see that on the inside of the ring, the B field is up in the way the current's going around this loop. All the little fields on the inside are going up, and on the outside are going down. So you get this like boosted effect of all the inside things are in the same direction and adding up. If I go from a ring to a coil, then I have ring after ring after ring with all the B fields on the inside going up, and I get this sort of more reinforcement of B fields. B fields tend to be kind of small and weak, but you can sort of boost their behavior by having them add up. So if you have a coil, then these B fields, these magnetic fields, sort of add up. Okay. Our next law of physics is that so the current gives rise to a magnetic field. If the magnetic field changes, it gives rise to an electric field. So that is the second law here, associated with some various names. And so a changing magnetic field causes an electric field. And then that electric field might cause a current, and that would be an induced current. So we have some original current and producing some magnetic field. And then if we try to change something about the magnetic field, that will produce a secondary or induced current. And I didn't bring my demo. Watch the slideshow, or I have a big magnet in my office. If you want to stop by, I'll give you a personal demo. But it's too hard on being online and doing demos. So, all right. Just a little side note about this effect and wiring of computers. If you have a sort of wired internet, so if you're in the room and you're at a computer that is connected with a physical wire to the internet with an Ethernet cable, then that wire does the opposite of what the coil does. So the coil tries to magnify the magnetic field, tries to boost the magnetic field by having all of the magnetic fields in the same direction and giving you a big effect. The wire in an Ethernet cable is twisted, and it makes the magnetic fields oppose each other and cancel each other out. So when you twist a wire, you are doing the opposite of coiling a wire, and you are trying to minimize the effect of a magnetic field. Because a magnetic field, a stray magnetic field will cause interference. Like when you suddenly turn on an air conditioner, that's a big change in a current and gives you a magnetic field and could cause some interference. But if you are twisting up your wire that's carrying your data that's very important to you, then it minimizes that effect. You can also shield it if you have a thicker cable, like your cable TV, there's a shielding. But in unshielded twisted pair, we don't shield, but we twist to minimize the effect. Okay. So now the effect that we're interested in is that we have a current that causes a magnetic field. And then if we try to change the current, that causes a changing magnetic field. And the changing magnetic field makes its own current. And that new current is opposite to the change. So it kind of tries to keep us from changing. It doesn't prevent us from changing. We're allowed to change, but it just makes it, it just kind of like resists the change. It's sort of like inertia, like having a mass. It's if you have a bigger mass, then it is harder to change its velocity. It's harder to get it to move faster, or it's harder to get it to move slower. So this effect is like that. It's analogous to inertia. I don't know if you've heard the phrase, things in motion tend to stay in motion, things that are still tend to remain still. That's inertia. And this is sort of an electromagnetic equivalent of that. This effect makes it harder to change currents. So if I had, I'm back to my coils because that's where my effect is big. So I have some coil with some current, and then I try to decrease the current, then the induced current is in the original direction. So I'm trying to reduce my current, but I'm trying to reduce my current, but my induced current, those are almost the same word, reduce and induce, but my induced current, my new secondary current, is in the original direction and tries to keep the current the same. It doesn't win, eventually the current gets changed, but at least slows down my change. If I were trying to increase my current and get a bigger magnetic field, that change would cause a current in the opposite direction. And so again, it won't stop me from changing the current, but it will sort of initially oppose me and make it a little bit harder to make that change and sort of slow down my change. If you have a device in a circuit that has the job of slowing down changes to the currents, that device is known as an inductor. They're sometimes also known as coils because that's their shape. They're shaped as a coil. And they're sometimes also known as chokes. So like in a car, you sometimes hear this referred to as a choke. The unit is a Henry, named after an American scientist who studied sort of like after Ben Franklin. He's the next sort of early American scientist who did some good work in electricity and magnetism. He was also the starter of one of the initial people in the Smithsonian Institute, so important early American scientist. Okay. All right. So here is a circuit with a switch and a resistor, and I'm showing you the oscilloscope, and you see that I flipped the switch and the current changed almost instantaneously. So it just blipped right up here. So I had no current, I flipped the switch, and then I have current. And I'm going to bring in an inductor next, and what an inductor is going to do is sort of slow down that change. Not prevent the change, but slow down the change. So here with the inductor, this little coily thing, this 1 Henry inductor here, I brought in and it slowed this down. You know and love this shape, or you know and hate this shape. This is the same shape for the RC circuits. So our 63% is back, our 37, if we're going down, is back. So if you didn't learn it the last time, learn it this time. If you learned it the previous time, good, it's the same. Now the oscilloscope is across the resistor, and here is the inductor, and there's a switch, and we close the switch, and there was no current, and then there's going to be current, but the change in the current is sort of spread out, and it's characterized by a time constant, which is related to the R and the L. So this is the same form that the voltage across the resistor has this sort of slow start saturating effect that we saw before. And there's a time constant tau. And there's also, if you flip the switch back, there's a decrease in the current, and it's an exponential decay. And then the tau is related to the R and the L, and you're supposed to sort of discover that a bit in the lab. Let me see if I can find that for you. Lab 11. What's 11A? 11A is an LR circuit. So that's what I just talked about. So here's the LR circuit, and then there's an LC circuit. So that's what I'm going to talk about next. But here I'm asking you first to keep the inductor fixed and change the resistance. When you're changing resistance, change it by a lot. Don't make it 1.2, 1.3, 1.4. That's not enough of a change. Make it like 1, 2, 3, 4, 5, or 1, 2, 5, 7, 10. You know, try to have some range of resistance so that it's not just a simple 1.1, 1.2, 1.3. That a small change and some inaccuracy in the simulation can get lost. Okay. And here's the time constant L on R. So you'll see the theory and the simulation, and I am asking you to vary R. Please vary R by a lot. Down here, you're going to vary I to L, which is called inductance, and vary it a lot. Okay. So now the next thing we're going to do is have a resistor, an inductor, and a capacitor together. So the first thing in this arrangement, when the switch is up, then the path is, let me do it this way. When the switch is up, where's my thick one, the custom? When the switch is up, this is just hanging there, and it's not part of the circuit, and the circuit is, customize the color. When it's up, here's the circuit. When the switch is up, there's the circuit. So it involves a resistor and a capacitor. And we know what a resistor capacitor looks like. It looks like that. Then when we're going down, the battery is not involved. And here's the circuit. So that's the circuit that we have to understand now. Okay. So the up part for this circuit, the up part is just an RC circuit, and we've done that before, and we're not going to do it again. But the down part, so here's the RC part of the circuit, which you know what that looks like. And then here's the LC part of the circuit, the inductor and the capacitor. And it's just this like solid looking block. That's not very useful. So we need to stretch out the time. So if you play with the time base, you can get this thing to stretch out, and it's like a sine wave. So it is an oscillatory behavior. Time-wise. All right. So when I get into this repeating behavior, the characteristic is the period or the frequency. The period is the time it takes to repeat. The frequency is how many times it repeats per second. So I go from one high to the next high, and it will do the subtraction for me, and that will tell me the period. And then the frequency is the reciprocal of the period, because the period is how many seconds for one oscillation for one cycle. So the period is the number of seconds for a cycle, and then the frequency is the number of cycles per second. So they're just one over the other. So here is my measured period. I went from one high to the next high. I could go from low to low. That would also work. And then I get the frequency by taking 1 on that. And the unit of frequency is inverse seconds, or also known as hertz. Okay. So we're going to charge the capacitor, and then the charged capacitor will want to get rid of its current. And so for the current to move off of it, we have to introduce a current. The inductor does not like changes in current, so it's going to resist that current changing off the capacitor initially. It doesn't like change. So here is my cartoon of an LC circuit. So the capacitor got charged. That's when we had the resistor and the capacitor, and the switch was in the opposite direction. And I put positive charges on one plate, negative charges on the other plate, and the positive charges don't like each other, but they like those negative charges on the other side. They can't move through the capacitor, so they must move through the inductor. So the positive charges that don't like each other say, let's get out of here. But the inductor says, slow down. I don't like to change. Doesn't mean it prevents the change. It just says, slow down. Don't make a big current all at once. So the current starts to come off of, the charges start to come off the capacitor. They start to form a current. And then that current sort of reduces the charge on the capacitor. That's what was causing the current in the first place. And so the current is coming off of the capacitor. So eventually at some point, so the current slowly built up. The charge slowly comes off of the capacitor. The current slowly builds up. And then the capacitor is happy. I don't have any positive charges that don't like each other anymore. I have a mix of positive and negative charges, which I'm happier about. But to do that, we set up a current, and inductors don't like change. So the inductor says, you got me going with this current, you better keep it coming. And so the inductor insists that that current keep coming. So now we start to do sort of the opposite of, we had positive charges on, we had too many positive charges on the plate. And then we got to the point where we were neutral. And now we're pulling positive charges off the plate to keep the current going. And we're leaving negatives behind. So we're charging the plate. We're now starting to charge the plate in opposite way than we had before. So now to keep the current going, the positives left what was neutral plate and left negatives behind. And so the current slowed down and slowed down and slowed down. And now the inductor has no current, so it's sort of happy, but the capacitor now has a bunch of negative charge on the top plate. And we sort of start all over again, but in the opposite direction. And so that's oscillation. You keep doing the same sloshing back and forth and back and forth. That's the oscillatory behavior. It will have a frequency. We saw that the circuit had a frequency, and we had, and the frequency then it just sort of comes up with on its own is what we call a natural frequency. We've also seen circuits that when we were playing, say, with diodes, we saw that we could have AC voltages. We could have voltages that also had a frequency, and that would be known as a driving frequency. So we can have two sort of frequencies going on here, the natural one of the circuit by itself, and then the driving frequency. So now I here's my inductor and my capacitor. That thing likes to oscillate. And now I've connected it to a signal generator, and that also oscillates. And so we have two sort of oscillations. The driver frequency always wins. So this guy's frequency wins. And so right now I'm putting in, this guy had a natural frequency, I think around 150, if I remember. Yeah, 152. But I'm putting in a 60 for a driver. And then when I run that circuit and figure out the period and the frequency, it's 60 or near 60. So the driver's winning. And it has, so that's the frequency. Another characteristic of a sine wave is its amplitude. How tall does it get? And so at this maximum point, it was 442 millivolts or 0.442 volts. So that's how big it is. That's its amplitude. If I move to 150, if my driver frequency is close to my natural frequency, I get a sine wave. But now I have an amplitude of 7.2 volts. I have a much bigger amplitude. Now I'm going higher than my 150. I'm above my natural. And let me run that. The frequency is about 200. Again, I tell you, the driver wins. And now the amplitude is 1.9. So the amplitude, when I'm lower than the natural frequency, is low. When I'm higher than the natural frequency is low. But when I'm at the natural frequency, the amplitude is high. This is known as resonance. when I have something that has a frequency, and then I can match its frequency, then I get a bigger effect. So I have something that oscillates sort of on its own, then I have some other thing that also oscillates, and if I get some matching up, then I get a big effect. This is important, say, it's important in a lot of things, but if you played music, then say trumpet or something like that, then you vibrate your lips a bit, but when you vibrate your lips, you're not controlling your frequency, you just have lots and lots of frequencies. But you set up your trumpet with the valves or whatever you do, and you set it up to have a natural frequency, and then one of the frequencies that you're putting into the trumpet matches the natural frequency of the instrument, and then you get that note has a big amplitude, and you hear the sound of the trumpet. And the same for other things, like if you blow across a flute, then that's all sorts of frequencies, but one of them gets picked up. And that's what will be important for us, is the ability to pick up one frequency among many, because that's going to make us a tuner, and that's going to allow us to have wireless computers. So I told you earlier in the day about wired computers. Now I'm going to tell you about wireless computers, that we send a signal out through the air. There are many signals out in the air. We need to be able to pick up the one we're interested in. Okay. Some time, all right. So a transmission. So I want to transmit a signal. I have an antenna. That's how I'm going to send a signal. I am going to put a wave into an antenna. And it's a wave, so it has changing. So I'm putting a current into a wire, and I am changing that current. I am putting, sometimes it's in one direction, sometimes it's another direction. So I have a changing current. So the current produces a magnetic field, but the changing current is going to produce a changing magnetic field. And the changing magnetic field gives us a changing electric field. That was one of those rules of physics. Now, when we want to send information, there's not much information in a sine wave. But what we do is modulate the sine wave. You change some feature of the sine wave to put your information. So you have the base sine wave is not interesting to us, but it carries our information. So the base sine wave is known as the carrier. And then we change a little something about it. And that's where our actual sort of data is. That's where our information is. Okay. But the main sine wave is definitely changing. And so we have a varying current, which is giving us a varying magnetic field. So the varying current gives us a varying magnetic field. A changing magnetic field gives us an electric field. That is also varying. Then the changing electric field gives us a magnetic field that's varying, and so on and so on. That is an electromagnetic wave. So the changing electric field gives a changing magnetic field, gives a changing electric field, gives a changing magnetic field. And that changing field spreads out from its original source, the transmitter, and so that information is getting carried. The information that was on the wave is being carried away. Okay. So we have this electromagnetic wave, and it's going through space. I'll say it goes through the air, but we don't really need air. We can send these signals through empty, through vacuums, through outer space. Okay. So we cause our wave, our antenna, our signal in our antenna causes this wave, and that signal is sent out. And other people are sending other signals. And so there are all these signals out in the world. And I need to be able to pick up the one that you're sending me because I want to listen to you. So we have this phenomenon of the electromagnetic wave happens at all sorts of different frequencies. And so lots of things that you think of as different things are the same thing. So if you listen to the radio, there are radio waves. If you cook in the microwave, that's the same thing. Infrared, like a heat lamp or something like that, that's the same. The light we can see, that's the same. Ultraviolet light, which will get you a nice sunburn, that's the same. You go to the doctor and get an X-ray. Those are all the same thing, just at different frequencies. But we want to be able to pick out, especially down here in say, if I want to listen to the radio, I want to pick out a signal that of my radio station. I don't want to listen to all the radio stations. I want to listen to my radio station. So we need a tuner. Well, we already saw a simple tuner in the LC circuit. We saw that when you drive an LC circuit, you get a big effect if you match the natural frequency. So we have some LC circuit, we sit it out there in the world with all these signals going on. The big effect happens if there's a signal that matches our natural frequency, then we get a big amplitude. Everything else is a small amplitude. So we sort of naturally, our natural frequency amplifies the one that we want and gets rid of all the other ones. So that is tuning in. So we can tune in our circuit. Now, I had information and I had it on a sine wave, and I want to get rid of the sine wave and just keep the information. So now I bring in a demodulator, and that is another job for a diode. So I can work with diodes and capacitors, and they will, a combination of a diode and a capacitor will get rid of the sine wave that was just carrying my information and help me separate my information from my carrier. I'm not going to have you do anything with demodulators. I'm just going to give you, here's an LC circuit, measure a period, compare it to a theory, be done. But I just want you to explain why these devices are useful. So here are two signals that are close in frequency. So this will give you a fast and a slow. If that's a phenomenon known as beats. So if you have two frequencies that are close but not quite the same, sometimes they're in sync, sometimes they're out of sync. And so there's a very fast part and a very slow part. Let me see if I can. And of course, they're showing me the headphones, which is not what I want to show you. That's what I want to show you. Here's a beat phenomenon of here's this very fast part and then a very slow part. So if I send that signal, so this is a beat signal, there's a fast part and a slow part. And then what I can do if I have the play with the right resistor and capacitor and diode, I can get sort of the slow part to just come out of this circuit. And then the final thing I need to do is then amplify my signal so that it is and that's a transistor thing. A transistor, we talked about, if you did that lab 9, you saw there was sort of an off region, an on region, and a sort of transition region. The transition region is the place where you work with a transistor if you wanted to amplify a signal. There's the last column in that table I make you make has a ratio of 2 currents. And there's a region that in the transition region, that ratio of those 2 currents is close to fixed. So you can put in a small current and get a bigger current. And so that is an amplification. Okay. So what do you want? Do you want me to start to talk about inductors and get all my talking done, or do you want to look at LC circuits? Say again? Get the talking done. All right. So let me talk about, I'll get all the talking done, but let me get some of the talking done. No. So let me talk about stacks. See how far I get in not quite 15 minutes. Okay. So stacks. Okay. So when we want to perform a calculation, we have to arrange the data and what we want to do with the data. So for a simple calculation, adding 4 and 5, we can arrange this in 3 ways. Let's say that we always want 4 to be before 5, so that takes out some of the combinations, but we can say 4, 5 plus. We can say, here's the first piece of data, the second piece of data, and we want to add them. We can do what's called prefix. We can say, here's the, what I want to do is add, put the plus sign, and then say, here's the 4, and then here's the 5. Or we can work with an infix notation and say, here's 4, and I want to add to that 5. And this is the way that we learn math. This is the notation we use when we learn math. But the way that computers are going to work is they need the data. The data has to be ready. So you had a circuit, I think it was lab 6, an adder with 2 registers, and you had to put 2 numbers in the register. You had to prepare the data, and then it got added. So this is the one that works well with hardware. Get the data ready, then you can perform an action on it. And when we have more complicated instructions with more numbers and more operations, we'll see that this postfix is good with a way of dealing with data that is known as a stack. So it is a protocol. Stack is a protocol for accessing information. Okay. So we have, when we are doing multiple calculations with multiple pieces of data, we have to worry about our precedence, our order of operations. And so if I have in infix 1 plus 2 times 3 minus 4, we have to remember that the multiplication comes first. So 2 times 3 happens first. It has a higher precedence, a higher order of operation. And then we're going to say we'll proceed. If we have equal operations like plus and minus, then we'll proceed from left to right, we'll say. But we're going to talk about the postfix, because that's the one that's good for hardware. You need to have the data before you can act on it. And also, it will lend itself to this thing called the stack that we can perform if we interact with the data by these rules known as the stack, then we can perform fairly complicated calculations. Okay, so the stack is basically a way to access data, and it obeys a certain rule known as LIFO. The last thing that goes in is the first thing that comes out. So our memory is random access. That means I can access it in any order. It doesn't matter when it came in or when it comes out. If that's what you want next, you can have it. Stack is different. The stack says you can only get the last thing you put in. The last, if you want a piece of data, it has to be the last one. That's the stack. So just here's it pictorially. I put a 1 was on the stack. If you put more data on the stack, that's known as a push. If you take something off, that's known as a pop. And you're always working at the top. Okay. Here's another picture. The stack pointer. So I don't move. I have some register, some collection of registers known as my stack. It may just be part of my memory. It often is. It's possible for it to be a separate from your main memory, or sometimes it's just a part of your main memory. But you're not going to like rearrange all the numbers in either way. You're not going to rearrange all the numbers. You're just going to. When we have memory, we have an address register, and that tells us where we're accessing data. And in the case of a stack, we have a stack pointer. So it tells us where we can access. So in this example here, it's pointing to the next available location. So if I have a 1, the stack pointer is pointing to the position next to the 1, above the 1 in this case. If I add the 2, the stack pointer moves. Okay. We can use this stack pointer to perform what's known as a postfix calculation. And so here is a postfix calculation, and I'm going to sort of show the stack performing this operation. So when you encounter a piece of data, you put it on the stack. And then when you encounter an operation, you'll take 2 things off the stack, perform the operation, and put the answer back on the stack. So this is how you calculate a postfix expression using a stack. So I'll go through this relatively rapidly. So 1 is data, I put it on the stack. 2 is data, I'm going to put it on the stack. 3 is data, I'm going to put it on the stack. The next thing I'm going to counter is the plus. It's an operation, not data. So I'm going to take the 3 off the stack and then the 2 off the stack. I'm going to push the 3. I'm going to pop the 3. I'm going to pop the 2. I'm going to perform the operation plus, get a 5, and I'm going to push the 5 onto the stack. 4 is data, onto the stack. I come across a multiplication, that's an operation. I pop off the 4, I pop off the 5, I perform the multiplication, get 20, and put it onto the stack. I come across a plus, it's an operation. I pop off the 20, I pop off the 1, I add them, I get 21, I put it on the stack. The 5 is data, I push. The 6 is data, I push. The plus is an operation. I'm going to pop off the 6. I'm going to pop off the 5. I'm going to add them. I'm going to put the answer 11 onto the bus. 7 is data. so I push. The 8 is data, so I push. The plus is an operation. I'm going to pop off the 8, pop off the 7, add them, and get 15. The 9 is data, I push. I come across a multiplication. 9, pop off the 9, pop off the 15, multiply them, and I don't know, 135. Then I run into another multiplication. So I pop off the 135, I pop off the 11, and do the multiplication, and that was 1485. Come across the plus, pop off the 1485 and the 21, perform the operation, put that on the answer. So this is, so there's a way, now you see that in postfix, there's no parentheses. It's the, if you're not ready to perform an operation, it just gets put onto the stack. It's just that the operator is going to occur later. So, where am I at? 2 or 3 minutes left. Okay. Well, we'll start. Okay. In a program, we have the program counter, which tells us where the next line of code is. And it is a counter so that it moves to the next line of code in memory. Sometimes the next line of code is not what our program wants to do. Sometimes our program wants to move around. And so if our program is not going to go to the next line of code, but to someplace else, that's known as a jump or a go to. So that's why the program counter has to be something that you can write to. If you ask a question and ask whether or not you jump, that's an if, and you can also make a loop out of it. So I can have a conditional jump. I'm going to jump here under some condition. So we can't do much coding without an if or without a loop. That's what computers are good at, making this, figuring out conditions, repeating themselves. So it wouldn't be much of a programming language if we didn't allow a conditional jump. The difference when you have a subroutine is that you're going to move, but you need to come back. So I need to, in the case of a subroutine or a function, I need to go someplace else, but I need the ability to come back. So I need to know where I was so that I can come back. I need to, Hansel and Gretel need to leave the breadcrumbs so that they can come back. That didn't work out so well, but so we need to remember where we were so that we can come back. So the difference between a subroutine at this low level, the difference between a subroutine and a loop or an if is that when I go someplace else in my code, I need the ability to come back, and I will leave it there. Finish talking about that on, I guess, Monday, but almost done all the blah, blah, blah. There's a lot of lab you can be working on. We're done all of 10. You can do at least half of 11. And part of 11 you can't do yet because I'm not done talking about stacks. You could probably do because it's one of those map out the instructions, so I tell you what to do. All right. Stop recording.